Okay, so I'm going to talk about a project that I did with some students with Christopher Everard, Kelly Johnson, and Nicole Regnier at Ball State, and it's called Using a Sand Tank Groundwater Model to Investigate a Groundwater Flow Model. So a sand tank groundwater model is a tabletop physical model constructed of plexiglass and filled with sand that is typically used to illustrate how groundwater flows through an aquifer, how water wells work, and the effects of the contaminants introduced into an aquifer. And mathematically, groundwater flow through an aquifer can be modeled with a heat equation. And we're going to show how a sand tank groundwater model can be used to simulate flow through an aquifer with no flow boundary condition. And this work appears as part of the third special issue of the Cody Journal, Engaging the World Differential Equations Can Influence Public Policies.
Thank you.
Okay, so one of the first partial differential equations that's encountered in the introductory course on boundary value problems is the one-dimensional heat equation. And typically, this equation is derived and introduced as a model for heat flow through a rod or bar made up of a homogeneous heat-conducting material with insulated lateral surface. And so let's consider a rod such as the one depicted in this figure 1 to the right. Let's assume the rod has uniform cross-section perpendicular to the x-axis, and that the temperature is the same at any point of this cross-section. And with this assumption, we can consider the temperature U in the rod to be a function of position along the x-axis and time, t. So U is a function of x and t. And so the diagram in figure 1 shows heat flowing from the right to the left through the rod. We're assuming that the temperature T1 is greater than the temperature T0, along with a small representative cross-sectional slice of width delta x and cross-sectional area A. Okay, so there's 4 possible contributions of heat to this cross-sectional slice. First thing is you can have heat flowing into the right face. You can have heat flowing out of the left face. You can have heat generated within the slice. And you can also have heat stored within the slice. And here, this Q of xt, that's taken to be positive when heat flows to the right. This is the heat flux, or the amount of heat per unit time per unit area flowing through the rod's cross-section at position x at time t. And the quantity G of xt describes the rate at which heat is generated within the slice. Rho is the density of the rod, and C is the heat capacity per unit mass. And both density and heat capacity can depend on x and t, but since we're considering the rod to be made up of homogeneous material, we're going to assume that these parameters are constant. Okay, so if you use the law of conservation of energy, which applied to the cross-sectional slice, that indicates that the heat flowing into the right face plus the heat generated within the slice is equal to the heat flow out of the left face plus the heat storage in the slice. We see for this scenario that we get this equation here. So these terms on the left are the heat flowing to the right face, the heat generated on the right side of the equal sign. You have the heat flowing out of the left face plus the heat storage. So if we rearrange the terms in equation 1 and divide by A times delta x, you get this relationship, and then you can let delta x go to 0 and 2. And so what you get is this. You get the derivative of q with respect to x is equal to a constant times the derivative with respect to t minus this generation term. So now we have a relationship between the heat flux and the temperature. And we want an equation that involves only the temperature, so we can use Fourier's law, which says that heat flux is proportional to the gradient of the temperature. And the proportionality constant kappa, that's called the thermal conductivity. And this could depend on x and t, but since our rod is homogeneous, we're assuming that kappa is constant. And the minus sign in 4, that indicates that heat flows from higher temperatures to lower temperatures. So if we substitute this negative kappa times the partial derivative u with respect to x for q of xt and 3, then what you get is this expression here. And then if we assume the thermal conductivity kappa is constant, we can divide 5 by kappa to get this relationship here, 6. And then if we define the thermal diffusivity K to be kappa over rho times C, then we would end up at the one-dimensional heat equation. So here's the one-dimensional heat equation, which relates the second derivative of temperature U with respect to X to the first derivative of U with respect to time T. And a common application of this heat equation is to find the temperature U of xt at any point X and any time T along the rod with a known initial temperature and specified boundary conditions, such as a fixed temperature at the end. And in some texts, one may also find applications that involve a fixed temperature at one end, and at the other end, it's insulated. So that means there's no heat flowing through that end. So one application of the heat equation that we haven't found in most boundary value problem texts is groundwater flow through an aquifer. And what an aquifer is, that's a water-bearing porous medium such as sand through which water flows easily. And instead of temperature, what we're interested in is the hydraulic head, H of xt. And you can think of this as the height of the water level relative to a reference point, such as sea level, at any point X at any time T along the aquifer. And just as with the heat conducting rod for applications, we need to specify appropriate boundary conditions and an initial condition. And instead of fixed temperatures or insulated boundary at each end and a known initial temperature distribution, there would be fixed head levels or a known flow boundary and known head levels at each point of the aquifer at a given time for initial information. Okay, so here's a table that illustrates that each aspect of heat flow in a rod has an analog in the groundwater flow through an aquifer setting. So in the left column, you have the components that go into heat flow in a rod. And so you have heat flux, temperature, Fourier's law, thermal conductivity, heat generation, there's a heat storage term, density, heat capacity, and thermal diffusivity. And then there's an analog for groundwater flow through an aquifer for each of these items. So there's volumetric flux, head level, Darcy's law, hydraulic conductivity, recharge, groundwater storage, specific storage, and hydraulic diffusivity. And just like we did for the heat conducting rod, we're going to assume that the aquifer is homogeneous, so that the parameters are constants that depend on the specific aquifer material. Okay, so for groundwater flow recharge, that describes the volume of water added per unit time per unit volume of the aquifer, and specific storage is the volume of water added to a release from storage per unit volume of aquifer per unit change in hydraulic head. And Darcy's law, which is the analog of Fourier's law in the groundwater flow setting, relates the volumetric flux or volumetric flow rate per unit cross-sectional area of the aquifer, that's the Q, to the gradient of the hydraulic head, and there's a proportionality quantity called the hydraulic conductivity. That's the K term. So if you use Darcy's law and the idea of continuity or conservation of mass, then you can essentially use the same argument we just saw above for deriving the one-dimensional heat equation. And we obtain a partial differential equation that describes hydraulic head level H at any point in an aquifer at any time. It's known as the one-dimensional groundwater flow equation. And here it is. And I guess we shouldn't be too surprised that this looks a lot like the heat equation. It's essentially the same thing. And here this hydraulic diffusivity K, that depends on the material in the aquifer through which the groundwater is flowing. So what we've just learned is that modeling groundwater flow is essentially the same as modeling heat flow. Okay, so what we have here is a sand tank groundwater model, and these are used to illustrate groundwater flow. This is a physical model. It's made up of plexiglass, two sheets of plexiglass with sand in between. And this is one that lives in the Ball State University's Department of Geological Sciences. And this is an educational device constructed of sturdy layered sand lenses to represent a sliced section of Earth. And sand lenses are just those little like lens-shaped pieces of material, like kind of near the middle, going from right to left in the aquifer. And through the use of water tinted with food coloring or grape Kool-Aid, it's possible to observe a wide range of groundwater movements. Okay, there's all the components that make up the groundwater um, sand tank groundwater model. And you can also use these things in an unconventional manner to tie together groundwater flow modeling and more advanced differential equations, concepts, and solution techniques. So what we're using this physical model for isn't something that people typically use it for. And so what we did is we left the sand tank in an unmodified state. And the reason I'm saying that is there's another experiment that I did with some other, a student and another colleague, where we actually opened up the drain hole and we had water flowing in on the right side at a fixed level and then flowing out at a fixed level. So that's a different model that we investigated for. So for this one, we left the plug in and we have water at a fixed height here by the right column here. And water is going to flow in and then it doesn't have anywhere to go. So that gives you the no flow boundary on the left-hand side. So then we added a drop of green food coloring to each well. So there's 3 wells we're looking at. This is the left well right here. Can you see my mouse?
Mm-hmm.
Okay, so there's
Yeah.
the left well, there's the middle well, and here's the right well. And you can see the water level in the wells is that's where the green food coloring column is, the top of it right there. So what we did is we there's a container with water and a little it looks like a gerbil feeder or something. So the water level is going to remain constant here on this side. It's going to flow in through the right end here, and this is called a recharge column here. And so what we did is we're using a physics software called Tracker. People use this to like film a ball moving through the air, and then you can click on the position of the ball frame by frame. So you can use this to illustrate ideas in a physics class. So we use this to frame by frame click, and we mark the top of the water level at each of these wells over time. So we did this for about 70 seconds worth of wellhead data. And that's about 30 frames per second for 70 seconds. So we collected data, and that's what this is Tracker, and here's the data that we're collecting over here on the right. Okay, so now we're looking at a model for our sand tank aquifer. And so figure 5 provides an illustration of a sand tank aquifer. So if you think back to the picture of the heat conducting rod, now we have this is like this is the aquifer. We have water at a head level H1 here, and we have a no flow boundary. So the water is going to flow from the right side to the left side of the aquifer. And a mathematical model for one-dimensional groundwater flow through this aquifer consists of the groundwater flow equation we just saw above, along with appropriate boundary conditions and an initial condition. And to simplify our model, we're going to assume that there's no recharge term in the groundwater flow equation. Okay, so here's an initial value boundary value problem that describes this specific situation right here. So equation 10, that's the groundwater flow equation. And then 11, that indicates a fixed head level of H1 at the right end of the aquifer. And then Darcy's law tells us that equation 12 saying there's no water flowing through the left end of the aquifer. And then equation 13, that's the initial head level at time t equals 0. So to guarantee a solution to this initial value boundary value problem, we assume that the function f of x, which describes the initial height of the water at each point along the aquifer, that's sectionally smooth. So that means f has a most finite number of removable jumps, discontinuities, and corners, with the function and its derivatives being continuous between such points. Okay, if you want to solve this initial value boundary value problem, you can use the standard technique of separation of variables. And you turn the problem into 2 ordinary differential equations to solve. And what you find is you get this series solution here, 14. It involves cosines and the exponential function. And here, these b sub n coefficients, you find those by integrating from 0 to a. And you're taking your initial temperature distribution minus the fixed head level at the right end. Okay, so to check our model, we use Mathematica to compare head level data for each well. The left, middle, and right wells collected from the sand tank to our model after specifying model parameters and initial data. So the aquifer is 23.75 inches long. So we let A be 23.75 inches. The head level at the right boundary when x equals a is measured to be 9.6875 inches. And since initial head levels at each well are measured to be 1.02919 inches, 1.16587 inches, and 1.39256 inches, this is at the left, middle, and right wells respectively. What we did is we just took the average of those head levels as our initial head level for our model. Okay, so with this choice by initial condition, the B sub n coefficients in 14 are found to be, well, you get a formula for finding the coefficients. You can stick in the H1 and H0, which we stated what those were on the last slide. We compute the coefficients, and then we set t equal to 0 in our series solution to determine an appropriate number of terms in the sum in equation 14 for our model. And we use graphical root mean square error and square error comparisons, and we found that a partial sum with 50 terms in our model should be sufficient. Okay, so here's a picture. So the red curve, that's our initial head level, and then this blue curve, that's just when I added in, I think, 50 terms. And so we're comparing a model at time t equals 0. We're sticking in 0 for t to the initial head level. And for the hydraulic diffusivity, we don't really know what kind of sand is in the aquifer, so we just chose a value for K to get a good graphical match between model and data, and then we use the minimization. We're basically doing a least square error minimization using mathematics find minimum commands. We're minimizing the root mean square error. And we also computed the root mean square error for, between the model and measured data for 1 to 100 terms to see how different numbers of terms impact the choice of K and resulting error. And what we find is the resulting root mean square error and choice of K are essentially the same for most choices of M, with the smallest error occurring when we choose 11 terms in our sum. And so for this reason, we chose 11 terms for our model. And figure 7 to the right shows that with K a little over 3 inches squared per second and a root mean square error of 0.45, 1039 inches, our model, it overestimates head level at the right well and underestimates head level at the left well. So the right well is right here, and then the middle, that's the middle well, and then the left well is this lower set of curves here. Okay, so one way to take into consideration the discrepancy between model and measured data at the right well is to treat fixed head level H1 at x equals a as an unknown parameter to be determined. So again, starting with choices of K and H1 to get a good graphical fit, followed by an application of find minimum in mathematics, we get a root mean square error of 0.297491 inches, with K is about 3.8 inches squared per second and H1 is 8.53 inches. What we can see is we get a much better fit for the right well, about the same fit for the middle well, but not a great match for the left well. So to see if we can get a better fit at the left well, we make another model revision by also treating the initial head level of another unknown parameter to be determined along with parameters K and H1 to minimize the root mean square error. And so in figure 9, we see that with these assumptions and K equal about 3.1 square inches per second, H1 is 8.696 and H0 inches, and H0 is about 1.82 inches. We get a much better match at all 3 wells. And this time the root mean square error has been reduced to about 0.2 inches. Okay, so we tried tweaking the model one more time to see if we can reduce the root mean square error. So we revised our model to include a recharge term, and this amounts to incorporating a new steady state and revised coefficients into our solutions. So what we get is this for our series solution. And here's how you find the B sub n's. And so with this revision, we get essentially the same results as we did for the second revision. K is about 2.8 square inches per second. H1, H0, those are about the same as before. The recharge term is 0.0007 inverse seconds, and the hydraulic conductivity is about 0.3 inches per second. And we get about the same root mean square error. And if you compare figure 10 to figure 9, you see they're virtually indistinguishable. So for fun, we thought we'd try a real world application. So from our model comparison to measure data results, it looks like it's clear that the heat equation can be used to model groundwater flow through an aquifer. So we thought, let's test our model. Let's consider the following real world situation. So let's suppose the groundwater in our sand tank is contaminated at time t equals 0 seconds, and we have a concern that it may impact 3 wells drilled for drinking water. The wells are located at these 3 positions in the aquifer, and they draw groundwater from an approximate head level of 4.4 inches. And using our model, we can answer these 3 questions. Does the groundwater reach any of these wells? If so, estimate the time at which the groundwater reaches these wells. How do these model time estimates, if any, compare to the actual time needed for the contaminated groundwater to reach the drinking wells? Okay, so this is a graph on figure 11, shows the model head levels at each drinking well location. So here is the right well, here's the middle well, and here's the left well. And then here's a height of 4.4 inches. So you can look at where the dotted line crosses each of these graphs, and then you can measure that. You can guess the times at which the groundwater reaches these wells. And so what we find is the contaminated groundwater reaches the left, middle, and right drinking wells at approximately 48 seconds, 30 seconds, and 4 seconds, respectively. And then you can use a fine root command in Mathematica to get a more accurate numerical estimate. So we get 49 seconds, 30.5 seconds, and about 4.4 seconds as the times when the contaminated groundwater reaches the left, middle, and right drinking water wells, respectively. Then we can check with tracker to see when the groundwater actually reaches the head level of 4.4 inches for each drinking water well. We find the actual times are approximately 63.5 seconds, 34 seconds, and about 7.3 seconds for the times they reach the drinking wells. Okay, so as a conclusion, using the Sand Tank Groundwater Model for an aquifer and collecting head level data with a video camera and tracker, we've been able to show that the one-dimensional groundwater flow equation can be used to model the head levels in the aquifer for the case when there's a fixed head level at one boundary and a no flow condition at the other boundary. And the results are surprisingly good to us, what we got, especially considering the fact that the aquifer we worked with does not have uniform material throughout. So here's some further questions. Regarding the real world question, we did notice that at each drinking water well, the actual times at which the wellhead level of 4.4 inches is reached in the aquifer are consistently greater than the times predicted by the model. And if you look at the Sand Tank Groundwater Model, the material at the bottom of the aquifer is different than the material at the level where the groundwater enters the drinking water wells. That's near the bottom. Our model assumes the aquifer material is homogeneous throughout. So a natural question that could be considered in the future investigations is, can we modify our model to take into consideration different materials in the aquifer at different levels? Another question to consider is perhaps our model needs to be modified to consider groundwater flow in more than one direction. Perhaps there is both horizontal and vertical movement of the groundwater through the aquifer. And when I'm talking about models here, I mean the mathematical models. And this would lead to a much more complicated mathematical model that is beyond the scope of this investigation. And one of the things to point out is these tanks are very expensive. We actually bought one for about $800. And so you don't want to mess with the material that's within the tank. So here's some implications for public policy. As pointed out in the Environmental Protection Agency's Handbook of Groundwater Protection and Cleanup Policies for RCRA Corrective Action, which is designed to help a regulator, member of the regulatory community, or member of the public find and understand EPA policies on protecting and cleaning up groundwater at Resource Conservation and Recovery Act corrective action facilities, such as Indiana's Department of Environmental Management. Groundwater supplies drinking water to half of the nation and virtually all people living in rural areas and supports many billions of dollars worth of food production and industrial activity. For this reason, it's crucial that policymakers are convinced that the mathematical models used to help investigating the cleanup of sites with contaminated groundwater are valid. And projects such as the one we just outlined can be used for this purpose. Okay, so that's basically the end of the talk. And then there's like 5 slides of references because I couldn't fit them all on one page. So that's it. Thanks.
Can I ask a question?
Sure.
Do you know for a fact that the standard heat equation diffusion model, is that a good model at the most basic level for water diffusing through a medium like that?
I'd say for one-dimensional flow, yeah, if you have a homogeneous medium, yes.
Okay,
There's lots of other way more complicated models that they use, but
yeah, I've seen like models for other things that you think would be good with a linear model, but like slow diffusion and fast diffusion, where it doesn't obey the usual heat equation. I wondered if that applies here or not.
Yeah, I don't know. I mean, I live in the world of simple stuff, and
That's not that simple.
or simple models. To me, this is a simple model. So
yeah, okay.
Mike, do you have any video of? You probably can't access it fast if you do, but
yeah, do you want me to pull it up? When you say video, you mean of the actual
the green
Oh, sure.
flowing up? That would be wonderful.
Let me see if I can get that.
I think I've seen it once.
Okay, so let me find let me see if I can get it working here. You know, I got to share my screen.
Yeah, sorry I didn't give you advance warning.
Okay, just to pause it here. Okay, I want to share my screen. How do I do that? Go here, share screen. Can everybody see that?
Yes.
Okay, so what you're gonna see is there's no water in the wells right now, or there's very little. It's near the bottom here. So I'm gonna run the video, and you're gonna see we're gonna turn the container of water upside down in the right, and then the water is gonna come in. Okay, here it comes.
Mm-hmm.
And now you can watch the water already in the right well. It's already growing pretty quickly at the head level.
Mm-hmm. Still going.
Yeah, so the students I gave them this project, and they rented a video camera from the library and collected all the data, and then I had them try setting up the model. I mean, the stuff I worked on, the more complicated models, they didn't see any of that, but they tried setting up the model and comparing the data and stuff. So I think it was a nice project for them. So and I should point out, this was funded by Indiana Space Grants Consortium grant, and so that I got this with Ken Luther from Valparaiso, and so the work the students did was funded by that grant.
Very good.
And also I if you go to the link for the paper, I also did this. Just I actually worked out the solution in Excel, so you can use Excel along with the solver that's built into Excel instead of Mathematica, and you get essentially the same results if you use that.
That's a good point.
Okay, so
Huh.
any other questions anybody has? Hey, Chris.
It's not a question, it's I guess a comment. A few years ago, a chemical engineering friend of mine was doing an experiment using a sand column. So you've got your sand column like this, and you've got the water's got a pollutant in it, and you flow the waters through the sand column, and the sand's removing the pollutant. You can model that as a diffusion equation for the pollutant, and then you've got a removal term because the sand's picking up the pollutant. So you might find that an interesting one to model, because that's just a heat conduction equation with a removal term.
Can you send me something a paper? Is there?
Yeah, I'll see if I can find the paper that had the experimental data in it and send it to you.
Okay. Thank you. So am I supposed to end the talk now? Or I don't know what I'm supposed to do at this point.
When nobody wants to say anything else, then you can just
Okay,
the meeting and that shuts it off.
Okay.
Do you want to say something, Chris?
Chris is muted.
I really like the this setup that you have. Is there, you didn't build it, you got that from the geology department?
Yeah, and we bought one, so we used the grant money to buy one. So in the links, there's like Iowa State at a like a geology club or something used to build these things. So we actually spent like $800, I think, to buy it with our grant money.
Uh-huh.
I never actually used that, but I actually used the one from geology before we had any of the money. We actually we used the one they had set up, and so they use them to illustrate like putting some contaminant in a lagoon or leaking, and then you can pump wells and you can watch the food colored water flow through the aquifer. So again, we were doing something different than how these are actually intended to be used. So
Oh, I like it. I want to get one for myself, maybe for Christmas. All right.
Chris,
Yeah, go ahead.
are you in that background?
No, this is, no, I'm at home. That's a picture up in Harriman State Park.
Ah.
One of the lakes frozen over. But,
Cool.
it's not today. That's one of the lakes on Seven Lakes Drive. I mean, you've been up there, right? To Bear Mountain, Harriman State Park?
Long ago, yes.
Michael, I just want to say that I love your paper.
well, thank you.
Yeah, I wasn't able to watch because I was in another room,
Okay.
but I watched the recording of your presentation here.
Okay, thank you. And I want to say to my Beverly and Samir, I really appreciate your input. This paper turned out, it's really nice. I mean, I really liked the way it turned out. So
Well, we gave you a bit of a hard time, but thank you
That's
for
okay.
responding.
yeah, but it turned out even way better than I expected it would. So
How many revisions did you make him do?
2 or 3.
That's not so bad.
But yeah, but it turned out really nice. So
That's in the latest issue of Cody?
yeah,
In the
Yes.
special issue, yes.
Yeah.
It's up now.